Hello everyone, today we're excited to present an in-depth exploration of the conceptual architecture of Flight Gear, an open-source flight simulator renowned for its versatility and realism. Introduction and Overview. Flight Gear stands out as a testament to open-source innovation and volunteer collaboration. As a free flight simulator, it offers an accessible platform for enthusiasts and developers alike. Our focus today is to provide an overview of Flight Gear, highlighting its open-source nature, volunteer-driven development, and its status as a premier free flight simulating tool. In this presentation, we'll go over the derivative process, the system architecture, the use cases, the evolution history, the development impact, and the lessons learned. Diving into the heart of Flight Gear's architecture, our journey began with a comprehensive derivative process. This involved an immersive engagement with the simulator coupled with an in-depth analysis of its documentation. Our goal was to peel back the layers of Flight Gear's complex system to understand its operational essence. Our hands-on approach allowed us to experience Flight Gear's functionality firsthand, bridging the gap between theoretical knowledge and practical application. Through meticulous research, we pieced together a picture of Flight Gear's modular design, revealing how its components interact and coalesce to form a cohesive simulation environment. This process illuminated the project's commitment to modularity, enabling us to appreciate the elegance of Flight Gear's architecture and the flexibility it offers to developers and users alike. Overall, the derivative process not only deepened our understanding of Flight Gear's inner workings, but also highlighted the simulator's adaptability and its open-source community's innovative spirit. System architecture. At the core of Flight Gear's robust and responsive design are two fundamental architectural styles: implicit invocation, also known as pub/sub, and client-server architecture. These frameworks are instrumental in achieving Flight Gear's high degree of modularity and real-time performance. The pub/sub architecture enables a decoupled communication model where components interact without direct knowledge of each other. Publishers broadcast events, and subscribers receive updates based on their interests. This model enhances Flight Gear's flexibility, allowing for dynamic updates and scalable system integration. Complementing the pub/sub model, the client-server architecture underpins Flight Gear's multiplayer functionality. It facilitates a structured interaction between users and the simulation environment, ensuring a synchronized and cohesive experience across the network. This architecture is key to managing complex, real-time interactions among multiple users, providing a seamless and consistent simulation. A standout feature of Flight Gear is its multiplayer operation. Concurrency in Flight Gear allows more than one user to interact with the simulation at the same time. Flight Gear employs the following two techniques to support concurrency. The first is multi-threading. The backend is coded using multi-threading, which will spin off multiple threads for each user session. And the second is input-output. Input-output operations are performed in a non-blocking model. That's why they are not waiting for the operations to return, including access to data and communicating over a network, which is better able to serve concurrent requests for operation. Flight Gear's development is profoundly influenced by two key principles: modular architecture and quality assurance. These principles not only define the project's approach to building a versatile flight simulator, but also ensure its ongoing improvement and reliability. The modular architecture of Flight Gear enables developers to innovate and refine components independently. This flexibility supports a dynamic development environment where enhancements and updates are seamlessly integrated, fostering a culture of continuous evolution. Quality assurance stands at the core of Flight Gear's development, ensuring the simulator meets high standards of performance and reliability. Through community-driven testing and feedback, Flight Gear maintains its commitment to delivering an exceptional and stable simulation experience. Together, modular architecture and quality assurance are crucial for Flight Gear's success. They empower developers, enhance the simulator's quality, and guarantee Flight Gear remains a leading open-source project in flight simulation.
Alright, so now we're going to talk about the dependency diagram, and we're just going to talk more about the general dependency diagram. So we're going to talk more, as the diagram shows, we have the user part, and then we've got the client client module, and then we've got the database, the RTI managers, the multiplayer manager, and then the server. So the user is any user that can engage with the program, and then the client manager is the main system in charge of client-side input. All stored file The database is the all stored information that such as airplanes and airport and the environment data. And when we focus on the RTI manager, it's the system that manages the relation in real-time infrastructure, modules, database, and the projects manager. And then with the multiplayer manager, when operating in multiplayer mode, it sends and receives data from a selected online server. Server is an off-client server that is designed to connect to program instances over the internet. Now let's focus more on the client modules. So in the client modules, we've got the GUI renders, the viewer renders, the weather sim, and AI traffic, and the FDM server. So when we're looking at the GUI render, it's about the graphic user interface and how we can enhance it to make it more usable for the users to use. And then when we're looking at the viewer's render, it's about the view and how it can enhance the view of the software or of the program to make it nicer to look at and make it easier for also for the user to interact with. And then the weather sim is basically a simulation of weathers that is given by the data set. So it's basically showing if it's rainy, if it's cloudy, if it's whatever it is. And then the AI traffic sim is basically simulates the AI planes if they are enabled. And then the FDM server is a flight dynamic model that simulates the physics behind the flight. Alright, so we've got the use case. First use case we've got is the starting game engine. So through when we were coming up with the use case, the first use case that we had in mind, or especially Josh that had it in mind, was the starting game engine. So Josh told us, how about the state when the user is able to fly an airplane? And we're like, that's an amazing one, because then we can use that diagram. So the dependency diagram. So the diagram here shows how the system generates a launcher or launcher GUI before starting the game engine. And then also the game engine is made up of all simulator and renders working together. So you've got the client manager, the GUI render, the database, the RTI manager, the view render, AI simulator, weather, and etc. But we can see over here in the diagram how the user, when it starts the program, it goes to the client manager, and then from the client manager, it goes all the way to the RTI manager, and so on. It shows how it goes back and forth until it makes sure that the game engine starts. And then the second one that also Josh came up with it was updating the database through the launcher. And we looked at it and we saw how nice and good idea that is of the use case. Which is also when you're looking at the website or the simulator, you have to make sure that the database stores the aspects like airplane models and airplane locations, scenery maps, and etc. These can be edited manually through the files or through the launcher. After the launcher is set up, the user navigates it and selects the aspect they wish to change. The GUI does not directly access the database, and that I'm reading right now off the slides, but it is cool looking at it and seeing how we can be updating the database through the launcher, and we can change stuff manually. All right, and for the evolution system of the foundation went from 1996 to the 2000, which initiated in 1996 with the 2D and 3D graphic simulation goals, and in 1997 it launched the Flight Gear's first version. In 2001 to 2010, it expanded and enhanced. So in version 0.7 and 0.9, it enhanced the flight dynamics, detailed models, and expanded global scenery. And then in version 1.0 and 2.0, it shifts to the OSG for better graphics and performance, introducing of realistic features like 3D clouds and AI traffic. Okay, and for the evolution system, we've got from the 2011 to the present, it's a continuous refinement. So it's improved UI and realism. It has a better AI traffic control. And then from the 2016 to the present, we focused more on performance, realism, and compatibility. So the key takeaways is the evolutionary milestones, which is the basic simulation of comprehensive and realistic flight simulation platform. And then the technological shifts, which is the significant shifts from adopting the OSG, have catalyzed flight gear's development, enhancing its capabilities and user experience.